I'm so glad you found your way here. Your body is made of the same dust that formed Earth 4.5 billion years ago. Tonight, you'll discover how emptiness becomes worlds, and by the end, you'll understand why planets are the universe's way of organizing chaos into beauty. Welcome to Get Sleepy Science. Wherever you are right now, perhaps feeling the solid ground beneath you, or gazing at planets shining in the night sky, allow yourself to rest in this cosmic stillness. We'll drift through 100 space facts about how planets are born. From clouds of gas collapsing in darkness, to dust grains sticking together grain by grain, to the moment a world first opens its eyes to starlight. These quiet journeys through space create a cosmic community of peaceful minds. Feel free to like and subscribe, or share a thought down in the comments. It helps others find their way here too. One sleepy soul at a time. It means the universe to us. Settle deeper into your pillows now. Let your shoulders drop, your breathing slow and steady. You don't need to hold on to any of this cosmic knowledge. Just feel that peaceful heaviness spreading through you, like you're floating weightless in the vast, silent darkness between stars, drifting gently towards sleep. Close your eyes and breathe deeply. You're floating where starlight paints pathways through infinite space. Let your mind drift with cosmic silence. And now we begin. Planets form from the leftover material surrounding newborn stars. When you look up at the night sky and see planets like Jupiter or Mars, you're witnessing the end result of a process that began over 4.5 billion years ago in our solar system. Every planet, moon, asteroid, and grain of cosmic dust started as part of a massive cloud of gas and dust floating in space. According to observations from the James Webb Space Telescope in 2024 and 2025, we now know this process is happening around thousands of young stars across our galaxy right now. The Atacama Large Millimeter Array in Chile has photographed these planetary nurseries with unprecedented clarity, showing us planet formation in action. These images reveal delicate rings and gaps in dusty disks, the telltale signs of planets being born. It's a reminder that world-building is not a rare cosmic accident, but a natural consequence of star formation, happening constantly throughout the universe. The process begins with a nebula, an enormous cloud of gas and dust drifting through interstellar space. These clouds can stretch for dozens or even hundreds of light years, containing enough material to form thousands of stars and their planetary systems. Our own solar system formed from such a cloud, called the solar nebula, approximately 4.6 billion years ago. Scientists have determined this age by studying meteorites that fell to Earth, which contain tiny mineral grains that formed during the solar system's earliest moments. The solar nebula was composed mostly of hydrogen and helium, the lightest and most abundant elements in the universe, left over from the Big Bang. But it also contained heavier elements like carbon, oxygen, silicon, and iron, forged inside previous generations of stars that lived, died, and scattered their ashes into space. Without those ancient stellar deaths, there would be no planets, no rocks, no life. We exist because stars died. Something gently disturbs the nebula, inviting the collapse to begin. A nebula can float peacefully through space for millions of years, remaining stable and diffuse. But planet formation requires a trigger, a disturbance that causes the cloud to begin contracting under its own gravity. Recent research suggests several possible triggers: the shockwave from a nearby supernova, the explosion of a massive star, can compress a nebula enough to start gravitational collapse. The spiral arms of our Milky Way galaxy, rotating slowly through space, can squeeze nebulas as they pass through these denser regions. Even the meeting of two nebulas can provide the necessary push. Evidence from isotopic analysis of ancient meteorites, published in studies from 2023 and 2024, suggests that our solar nebula may have been compressed by a nearby supernova explosion. Tiny grains found in meteorites contain radioactive isotopes that could only have been produced in a supernova and delivered to our forming solar system within a few million years. We may owe our existence to a star that exploded nearby billions of years ago. Gravity begins pulling the nebula inward toward its center. Once the collapse begins, gravity takes over as the dominant force. The center of the nebula, where the most mass is concentrated, pulls material inward from all directions. As the cloud contracts, it heats up. This may seem counterintuitive, but it follows a fundamental law of physics discovered by Lord Kelvin and Hermann von Helmholtz in the 19th century. When gas is compressed, its temperature rises. This is the same principle that makes a bicycle pump warm when you inflate a tire. In the collapsing nebula, gravitational potential energy converts into thermal energy, or heat. The center of the cloud becomes hotter and denser, while the outer regions remain cooler and more diffuse. This temperature difference will ultimately determine where different types of planets can form. Rocky planets like Earth will form closer to the center where it's hot, while gas giants like Jupiter will form farther out where it's cold. The architecture of a planetary system is written in its temperature map. The nebula begins to spin faster as it contracts. This is due to the conservation of angular momentum, one of the most fundamental principles in physics. Angular momentum is the rotational equivalent of linear momentum. Just as an object in motion tends to stay in motion unless acted upon by a force, a rotating object tends to keep rotating. When the nebula contracts and becomes smaller, it must spin faster to conserve its angular momentum. You can see this same principle when an ice skater pulls their arms inward during a spin, rotating faster and faster. The solar nebula, initially rotating very slowly, began spinning faster and faster as gravity pulled it inward. This rotation prevented all the material from falling straight into the center. Instead, the cloud flattened into a disk shape, with most of the mass concentrated at the center and a thin disk of material orbiting around it. This is why planetary systems are flat, why all the planets in our solar system orbit roughly in the same plane. The disk structure is a natural consequence of rotation and gravity working together. The center of the disk becomes the Sun, and the outer disk becomes the planets. About 99% of the nebula's mass collapsed into the center, where temperatures reached millions of degrees. At these extreme temperatures, hydrogen atoms began fusing together to form helium, releasing enormous amounts of energy. This is nuclear fusion, the process that powers all stars. Our Sun was born. The remaining 1% of the nebula's mass spread out in a flat, rotating disk around the newborn star. This is called a protoplanetary disk. Observations from the Hubble Space Telescope and the James Webb Space Telescope have captured stunning images of protoplanetary disks around young stars in nearby star-forming regions like the Orion Nebula and the Taurus Molecular Cloud. These disks range from a few billion miles to several hundred billion miles in diameter. Within these disks, the material that will eventually become planets begins its long journey of assembly. The disk is not smooth or uniform, but contains complex structures, rings, gaps, spirals, and clumps. Each of these features tells a story about the physical processes shaping the disk and the planets forming within it. The temperature of the protoplanetary disk varies with distance from the Sunday close to the newborn star. Temperatures reach thousands of degrees, hot enough to vaporize rock and metal. Farther out, beyond a certain distance, temperatures drop below the freezing point of water, allowing ice to form. This boundary, called the frost line or snow line, plays a crucial role in determining what types of planets can form at different distances. In our solar system, the frost line was located roughly where the asteroid belt is today, between the orbits of Mars and Jupiter, about 2.7 astronomical units from the Sunday. 1 astronomical unit is the average distance between Earth and the Sun, about 93 million miles. Inside the frost line, only materials that remain solid at high temperatures, like silicate minerals and metals, could condense from the hot gas. These became the building blocks of rocky planets like Mercury, Venus, Earth, and Mars. Outside the frost line, water ice, ammonia ice, and methane ice could form, in addition to rock and metal. These icy materials are much more abundant in the universe than rock and metal, so there was far more solid material available beyond the frost line. This abundance of material explains why the outer planets grew so much larger than the inner planets. Dust grains in the disk begin sticking together through a process called accretion. The disk contains microscopic particles, typically less than a micrometer in size, about 1/100th the width of a human hair. These tiny grains are composed of silicate minerals, carbon compounds, and in the colder regions beyond the frost line, ice. The grains collide with each other constantly as they orbit the Sunday. Some collisions are gentle enough that instead of bouncing apart, the grains stick together. This sticking is aided by several forces. Electrostatic forces, similar to static electricity that makes a balloon stick to a wall, can cause dust grains to cling to each other. Van der Waals forces, weak attractive forces between molecules, also help. Additionally, the grains may have sticky coatings of organic compounds or ice that act like glue. Laboratory experiments conducted by planetary scientists, including recent studies published in 2024, using parabolic flight experiments to simulate microgravity, have demonstrated that dust grains can indeed stick together under the conditions present in protoplanetary disks. Slowly, grain by grain, microscopic particles grow into larger aggregates. This is the first step in building a planet from dust. These growing clumps of dust are called planetesimals, the seeds of planets. As dust grains stick together, they form larger and larger objects. When they reach sizes of about half a mile to several miles across, we call them planetesimals. Think of them as cosmic boulders, small protoplanets orbiting the young Sunday. The transition from dust grains to planetesimals is a curious puzzle in planetary science, sometimes called the meter-size barrier. When objects grow to the size of pebbles or boulders, they experience strong aerodynamic drag from the gas in the disk, causing them to spiral inward toward the Sun very quickly, within just a few hundred years. This should prevent them from growing large enough to become planets. However, we exist, and planets clearly form, so there are mechanisms that overcome this barrier. Recent research, including computer simulations published in 2024 and 2025, suggests that turbulence in the disk, gravitational instabilities, or local concentrations of dust can help objects jump across the meter-size barrier more quickly. The details are still being worked out, but it's clear that planetesimals do form, following pathways we're still discovering, and they become the building blocks of everything that follows. So yes, we're already seeing how planets form from nothing but gas and dust. The nebula collapses, spins faster, flattens into a disk. Dust sticks together grain by grain. Small becomes large. Diffuse becomes solid. From emptiness, structure emerges. From chaos, order is born. The early solar system was a busy place, a disk of swirling material gradually organizing itself into the architecture we see today. And the story continues, gently unfolding. Planetesimals are just the beginning. Planetesimals continue to collide and merge, growing into larger bodies called protoplanets. Gravity. Even the weak gravity of small planetesimals begins to play a role. Larger planetesimals have stronger gravity, which helps them attract and capture smaller ones nearby. This creates a runaway growth process. The bigger an object gets, the faster it grows. Computer simulations of the early solar system show that within a few 100,000 years, a disk containing millions of planetesimals can produce a smaller number of much larger protoplanets, objects ranging from the size of the Moon to the size of Mars. These protoplanets are not yet true planets, but they're well on their way. Collisions between protoplanets are violent events, melting rock, vaporizing ice, and sometimes shattering both objects into fragments that must reassemble. The process is messy, chaotic, and spectacular. The inner solar system forms rocky planets through high-energy collisions. Mercury, Venus, Earth, and Mars all formed within the frost line, where temperatures were too high for ice to condense. These worlds grew by accumulating silicate rock and metal. Studies of isotopic compositions in Earth's rocks and meteorites, including research published in 2025, suggest that Earth formed rapidly, reaching most of its current mass within 10 to 20 million years after the solar system began forming. This is remarkably fast on cosmic timescales, but the process was violent. Earth experienced countless impacts from planetesimals and protoplanets during its formation. The heat generated by these impacts melted the entire planet, creating a global magma ocean hundreds of miles deep. Heavy elements like iron and nickel sank toward the center, forming Earth's iron core. Lighter silicate minerals floated to the surface, forming the mantle and eventually the crust. This process, called differentiation, transformed Earth from a homogeneous mixture of rock and metal into a layered structure with a distinct core, mantle, and crust. All rocky planets underwent similar differentiation early in their histories. The Moon formed from a giant impact between Earth and another protoplanet. This is one of the most dramatic events in our planet's history. About 4.5 billion years ago, after Earth had already grown to roughly its current size, it encountered another Mars-sized protoplanet that scientists call Theia. The ancient meeting was cataclysmic. Computer simulations show that Theia struck Earth at an oblique angle, not head-on. The impact vaporized both Theia's mantle and a large portion of Earth's mantle, sending an enormous spray of molten and vaporized rock into orbit around Earth. This debris quickly coalesced, within perhaps just a few days to months, forming the Moon. Evidence for this giant impact hypothesis comes from several sources. Moon rocks brought back by Apollo astronauts have the same isotopic composition as Earth's mantle, indicating they came from the same source material. The Moon has very little iron compared to Earth, which makes sense if it formed primarily from the rocky mantles of Earth and Theia, while the iron cores merged into Earth. Recent refinements to the giant impact theory, published in 2024, suggest that multiple smaller impacts may have contributed to the Moon's formation, but the overall picture remains the same. Our Moon was born from violence, from an encounter so powerful it nearly destroyed Earth itself. Beyond the frost line, planets could grow much larger by incorporating ice. In the cold outer regions of the solar system, beyond about 2.7 astronomical units from the Sun, water ice remained frozen. Ice is much more abundant in the universe than rock or metal because oxygen is a common element and readily combines with hydrogen, the most abundant element, to form water. This meant there was far more solid material available to build planets in the outer solar system. Jupiter, Saturn, Uranus, and Neptune all formed beyond the frost line. These worlds grew large enough to gravitationally capture hydrogen and helium gas from the surrounding disk, becoming gas giants and ice giants. The process began the same way as the inner planets, with dust and ice grains sticking together to form planetesimals and protoplanets. But because there was more material available, these planetary cores grew much larger, reaching masses 10 to 20 times that of Earth. Jupiter's core grew so large, it began capturing gas from the disk. Once a planetary core reaches a critical mass, about 10 times Earth's mass according to current models, its gravity becomes strong enough to pull in the lightweight gases, hydrogen and helium, directly from the surrounding protoplanetary disk. This process is called gas accretion. Jupiter's core, composed of rock and ice, reached this critical mass and began rapidly pulling in gas. Within perhaps just a few million years, Jupiter had grown to its current size, about 318 times more massive than Earth. Most of Jupiter's mass is hydrogen and helium gas, not the rock and ice core that started the process. Saturn formed in a similar way, though it captured somewhat less gas, making it less massive than Jupiter. Observations from the Juno spacecraft, which has been orbiting Jupiter since 2016 and continues to return data through 2025, have provided detailed measurements of Jupiter's interior structure, confirming that it has a dense core of heavy elements, surrounded by an immense envelope of hydrogen and helium. These giant planets played a crucial role in shaping the entire solar system. The gas giants likely migrated from their original orbits after forming. This discovery has quietly reshaped our understanding of how planetary systems evolve over time. Planets don't necessarily stay where they form. Gravitational interactions with the gas and dust in the protoplanetary disk, as well as gravitational interactions with other planets, can cause planets to drift inward or outward over time. Computer simulations of the early solar system suggest that Jupiter formed farther from the Sun than it is today, perhaps at a distance of about 5 to 10 astronomical units, and then migrated inward. Saturn also migrated, and the two giant planets eventually became locked in an orbital resonance, where their orbital periods were related by a simple ratio. This migration stirred up the entire solar system, scattering planetesimals and smaller bodies throughout the inner and outer regions. The Nice model, named after the French city where it was developed, suggests that this migration and the subsequent gravitational instability between the giant planets explains many features of our solar system, including the orbits of the outer planets, the populations of asteroids and comets, and even the late heavy bombardment, a period about 3.9 billion years ago, when the inner planets experienced an intense spike in impacts. Uranus and Neptune formed differently than Jupiter and Saturn. These two planets are often called ice giants rather than gas giants because they're primarily composed of heavier elements, not just hydrogen and helium. Uranus and Neptune each contain much more water, methane, and ammonia than Jupiter or Saturn. Their cores are larger relative to their total mass, and their gas envelopes are thinner. Current models suggest that Uranus and Neptune formed closer to the Sun than they are today, perhaps in the region between Saturn and Uranus's current orbit. They didn't grow fast enough to capture enormous amounts of hydrogen and helium before the gas in the disk was blown away by the young Sun's intense radiation and stellar wind. After the gas disk dissipated, gravitational interactions with Jupiter and Saturn scattered Uranus and Neptune outward to their current positions. This outward migration took millions of years and involved close encounters with countless icy planetesimals, many of which were either captured as moons, ejected from the solar system entirely, or sent inward toward the Sun, where they could impact the inner planets. The asteroid belt between Mars and Jupiter is composed of leftover planetesimals that never formed a planet. Early in the solar system's history, this region likely contained enough material to form a small planet. But Jupiter's immense gravity stirred up the orbits of planetesimals in this region, increasing their collision speeds. Instead of gently merging when they collided, the planetesimals shattered into fragments. Over time, most of the mass in the asteroid belt was either ejected from the solar system, sent into the Sun, or captured by other planets. Today, the asteroid belt contains only a tiny fraction of its original mass. The largest object in the asteroid belt is Ceres, a dwarf planet about 590 miles in diameter, large enough that its own gravity has pulled it into a spherical shape. Ceres is differentiated, with a rocky core and an icy mantle, and recent observations from NASA's Dawn mission, which studied Ceres until 2018, suggest it may even have a subsurface ocean. The asteroid belt serves as a museum of the early solar system, preserving primitive materials that have remained relatively unchanged for billions of years. The Kuiper Belt and Oort cloud are reservoirs of icy bodies in the outer solar system. Beyond Neptune's orbit lies the Kuiper Belt, a region containing millions of icy objects left over from planet formation. These are sometimes called trans-Neptunian objects. The most famous Kuiper Belt object is Pluto, which was reclassified as a dwarf planet in 2006. The Kuiper Belt extends from about 30 astronomical units from the Sun, Neptune's orbit, to perhaps 50 or 55 astronomical units. Even farther out, between roughly 2,000 and 100,000 astronomical units, lies the Oort cloud, a vast spherical shell of icy bodies surrounding the solar system. The Oort cloud has never been directly observed because these objects are so distant and faint, but its existence is inferred from the orbits of long-period comets, which come from all directions in the sky. Both the Kuiper Belt and Oort cloud represent the leftover debris of planet formation, material that was never incorporated into planets. These distant icy bodies occasionally get perturbed by gravitational interactions and fall inward toward the Sun, becoming the comets we see lighting up the night sky. The young Sun's energy eventually dispersed the remaining gas in the disk. Stars go through a highly active phase early in their lives called the T Tauri phase, named after the star where this phenomenon was first observed. During this phase, which lasts for a few million years, the star produces strong stellar winds and intense ultraviolet radiation. This energy blows away the remaining gas in the protoplanetary disk. Observations of young star systems in nearby star-forming regions show that most protoplanetary disks dissipate within about 3 to 10 million years. Once the gas is gone, gas giant planets can no longer grow by capturing hydrogen and helium. This sets a time limit on gas giant formation. Planets that don't grow large enough, fast enough, will remain rocky or icy worlds. The clearing of the disk marks the end of the primary planet formation phase. What remains is a solar system of planets, moons, asteroids, comets, and dust, still undergoing collisions and orbital adjustments, but the main structure is established. Impacts continued for hundreds of millions of years after the gas disk dispersed. The early solar system was a violent shooting gallery. Planets and moons were bombarded constantly by leftover planetesimals. Earth continued to grow slightly through impacts, and its surface was reshaped repeatedly. The late heavy bombardment, approximately 3.9 billion years ago, was a particularly intense period of impacts. Craters on the Moon dating from this time are still visible today. This bombardment may have been triggered by the orbital migration of the giant planets, which destabilized the orbits of millions of small bodies and sent them careening through the inner solar system. Some scientists have speculated that the water in Earth's oceans may have been delivered during this period by impacts of comets, and water-rich asteroids. This is still debated, but it's clear that impacts played a major role in the final stages of planetary evolution, shaping surfaces, delivering volatiles like water and organic molecules, and possibly even influencing the development of life. Planetary atmospheres formed through volcanic outgassing and impacts. As rocky planets like Earth underwent differentiation, heating from radioactive decay and impacts caused volcanism. Volcanoes released gases trapped in the planet's interior, including water vapor, carbon dioxide, nitrogen, sulfur dioxide, and other compounds. This process, called outgassing, created the first atmospheres on rocky planets. Earth's early atmosphere was very different from today's. It contained little to no free oxygen and was composed primarily of water vapor, carbon dioxide, and nitrogen. Some atmospheric gases may also have been delivered by impacts of comets and asteroids. Over billions of years, Earth's atmosphere evolved dramatically, particularly after photosynthetic life began producing oxygen about 2.4 billion years ago. Venus and Mars also underwent outgassing and developed atmospheres, though their evolutionary paths diverged from Earth's. Venus's thick carbon dioxide atmosphere created a runaway greenhouse effect, while Mars's thin atmosphere gradually eroded away over time. Understanding how planetary atmospheres form and evolve is crucial for understanding habitability. Some planets have magnetic fields generated by liquid metal in their cores. Earth has a strong magnetic field that protects the surface from harmful solar radiation and charged particles streaming from the sun in the solar wind. This magnetic field is generated by a geodynamo, a process where convection currents in Earth's liquid iron outer core, combined with the planet's rotation, create electric currents that generate a magnetic field. This is similar to how an electrical generator works. For a planet to have a magnetic field generated this way, it needs a liquid conducting layer in its interior and sufficient internal heat to drive convection. Earth, Jupiter, Saturn, Uranus, and Neptune all have active magnetic fields. Mercury has a weak magnetic field, likely generated by a partially liquid core. Venus, Mars, and the Moon do not currently have global magnetic fields, though Mars shows evidence of an ancient magnetic field recorded in its rocks, suggesting its core was once active. The presence or absence of a magnetic field can have profound effects on a planet's ability to retain an atmosphere and maintain habitable conditions at the surface. Moons formed through several different mechanisms throughout the solar system. We've already discussed how Earth's moon formed from a giant impact, but moons can form in other ways too. Some moons, called regular satellites, formed in orbit around their parent planet from a disk of material. Similar to how planets formed around the Sun, Jupiter's 4 large moons, called the Galilean moons, discovered by Galileo Galilei in 1610, likely formed this way. Other moons, called irregular satellites, were probably asteroids or comets that were gravitationally captured by a planet after the solar system formed. These moons often have retrograde orbits, meaning they orbit in the opposite direction to their planet's rotation, and highly elliptical orbits. Mars's 2 small moons, Phobos and Deimos, may be captured asteroids, though recent research suggests they might have formed from a debris disk created by a giant impact on Mars. Saturn's largest moon, Titan, is bigger than the planet Mercury and has a thick nitrogen atmosphere. Understanding how moons form gives us insight into the complex and varied processes of world building throughout the solar system. These observations reveal that planet formation is messy, chaotic, and incredibly diverse. No 2 planetary systems are exactly alike. Since the first exoplanet orbiting a Sun-like star was discovered in 1995, astronomers have found thousands of planets around other stars. These exoplanets show an astonishing variety of types, sizes, orbits, and compositions. Some are hot Jupiters, gas giants orbiting extremely close to their stars, completing an orbit in just a few days. Some are super-Earths, rocky planets larger than Earth but smaller than Neptune. Some orbit binary stars. Some have highly elliptical orbits. This diversity tells us that planet formation is influenced by many factors: the mass of the protoplanetary disk, the presence or absence of nearby massive planets, the timing of gas dispersal, the migration history of planets, and random events like giant impacts. The more we learn, the more we realize that our solar system is just one possible outcome among countless variations. And yet, the fundamental processes remain the same: gravity, accretion, differentiation, migration. From chaos, planets are born. Take a deep breath and feel this. Every atom in your body, the carbon, the nitrogen, the oxygen, the iron, was created in the core of a dying star. The dust that built Earth, that built your bones, traveled through space for millions of years before settling here. Feel yourself carrying the trace of ancient stars. Every breath you take, you're breathing recycled atoms from the very nebula that formed our Sunday. We are all made of planet-forming material, shaped by the same forces. Now we continue. Planetary cores are denser than their outer layers because of differentiation. When a planet is young and molten, either from the heat of formation or from radioactive decay, gravity causes denser materials to sink toward the center, while lighter materials rise to the surface. This is similar to how oil floats on water. In rocky planets, iron and nickel are denser than silicate minerals, so the metals sink to form a core, while the silicates form the mantle. Earth's core is about 85% iron, with some nickel and lighter elements mixed in. The core is incredibly hot, with temperatures at the boundary between the inner and outer core reaching about 9,000 degrees Fahrenheit, roughly as hot as the surface of the Sunday. The pressure at Earth's center is about 3.6 million times atmospheric pressure at sea level. Under these extreme conditions, the inner core is solid metal, despite the high temperature, because the immense pressure prevents it from melting. The outer core remains liquid, and convection in this liquid iron generates Earth's protective magnetic field. Gas giants have complex internal structures we're still working to understand. Jupiter and Saturn are sometimes described as failed stars because they're composed primarily of hydrogen and helium, the same elements that make up stars, but they never grew massive enough to ignite nuclear fusion in their cores. Jupiter's interior is divided into several layers. At the center is a core of rock, ice, and metallic compounds, perhaps 10 to 20 times Earth's mass. Above that is a thick layer of metallic hydrogen, a state of hydrogen that exists only under extreme pressures. In metallic hydrogen, the atoms are squeezed so tightly that electrons are stripped away, and the hydrogen behaves like a liquid metal, conducting electricity. Convection in this metallic hydrogen layer generates Jupiter's powerful magnetic field. Above that is a layer of liquid molecular hydrogen, and finally, at the top, a relatively thin atmosphere of hydrogen and helium gas. Saturn has a similar structure, but with proportionally less metallic hydrogen. Data from the Juno mission and the Cassini mission, which orbited Saturn from 2004 to 2017, have revealed that these giant planets may have fuzzy cores rather than distinct boundaries, with heavier elements gradually mixing with the hydrogen envelope. Planetary rotation rates vary widely and tell stories of ancient impacts. Earth rotates once every 24 hours, giving us our day-night cycle, but not all planets rotate at the same speed. Jupiter rotates once every 10 hours, making it the fastest spinning planet in the solar system. Its rapid rotation causes it to bulge at the equator, making it noticeably oblate, not perfectly spherical. Venus, on the other hand, rotates incredibly slowly, taking 243 Earth days to complete one rotation. Even stranger, Venus rotates backward compared to most planets, spinning in the opposite direction. This retrograde rotation may have been caused by a massive impact early in Venus's history that literally flipped the planet over. Uranus also has an extreme tilt, rotating on its side with an axial tilt of 98 degrees. During Uranus's year, which lasts 84 Earth years, each pole spends 42 years in continuous sunlight, followed by 42 years in continuous darkness. This extreme tilt was probably caused by one or more giant impacts during the planet's formation. These rotational quirks remind us that planet formation involves dramatic, sometimes catastrophic events. The spacing of planets in the solar system follows a rough pattern. In 1766, astronomers Johann Daniel Tisius and Johann Elert Bode noticed a simple mathematical relationship that approximately describes the distances of planets from the Sunday. This pattern, called the Titius-Bode law, predicted the existence of a planet between Mars and Jupiter, which led to the discovery of the asteroid belt. The law also approximately predicted the location of Uranus when it was discovered in 1781. However, the law breaks down for Neptune and doesn't work well for other planetary systems, so it's likely a coincidence rather than a fundamental principle. The actual spacing of planets is determined by the dynamics of the protoplanetary disk, the locations of orbital resonances where gravitational interactions are strong, and the migration history of the planets. Despite the lack of a simple mathematical law, the spacing of planets is not random. Planets tend to avoid certain orbits where resonances would destabilize them over time. Orbital resonances between planets can stabilize or destabilize planetary systems. An orbital resonance occurs when two orbiting bodies exert regular, periodic gravitational influences on each other, usually because their orbital periods are related by a ratio of small integers. For example, Neptune and Pluto are in a 3:2 resonance. Neptune orbits the Sun 3 times for every 2 orbits of Pluto. This resonance actually prevents Pluto from colliding with Neptune, even though their orbits cross. The resonance keeps them out of phase, so they're never in the same place at the same time. Jupiter's moons Io, Europa, and Ganymede are locked in a complex resonant chain called the Laplace resonance, where Io orbits 4 times for every 2 orbits of Europa and every 1 orbit of Ganymede. This resonance pumps energy into Io through tidal heating, making it the most volcanically active body in the solar system. Resonances can also be destabilizing. The Kirkwood gaps in the asteroid belt are regions nearly empty of asteroids because resonances with Jupiter eject objects from those orbital distances. Resonances are like invisible threads connecting planets and moons, shaping their orbits over millions of years. Some planets have rings, formed from destroyed moons or captured material. Saturn's rings are the most spectacular, stretching hundreds of thousands of miles across, yet only about 30 feet thick in places. The rings are composed of billions of particles of water ice, ranging from tiny grains to house-sized boulders. Observations from the Cassini mission revealed that Saturn's rings are relatively young, perhaps only a few 100 million years old, formed when a moon wandered too close to Saturn and was torn apart by tidal forces. Jupiter, Uranus, and Neptune also have ring systems, though much fainter than Saturn's. Jupiter's rings are composed of dust kicked up from its small inner moons by micrometeorite impacts. Uranus's rings are narrow and dark, composed of material that may have been darkened by radiation. Neptune's rings are incomplete, containing dense arcs of material. Rings are dynamic structures, constantly evolving. Material spirals inward toward the planet or outward into space. New material is supplied by impacts on moons or by the breakup of comets and asteroids passing too close. In a few 100 million years, Saturn's magnificent rings may be gone, spiraled into the planet's atmosphere. Tidal forces shape moons and planets over time. Tides are caused by differences in gravitational pull across an object. The side of Earth's oceans facing the Moon experiences slightly stronger gravity than the center of Earth, while the side facing away experiences slightly weaker gravity. This creates two tidal bulges, one facing the Moon and one on the opposite side. As Earth rotates beneath these bulges, we experience high and low tides. Tidal forces also cause friction, gradually slowing Earth's rotation. Billions of years ago, Earth's day was much shorter, perhaps only 10 hours long. The Moon is gradually moving away from Earth at a rate of about 1.5 inches per year, as energy is transferred from Earth's rotation to the Moon's orbit. Eventually, in billions of years, Earth and the Moon will become tidally locked, always showing the same face to each other. The Moon is already tidally locked to Earth, which is why we always see the same side. Tidal forces can also generate heat inside planets and moons through tidal flexing. Jupiter's moon Io is constantly squeezed and stretched by Jupiter's gravity and the gravitational influences of the other Galilean moons, generating enough heat to drive hundreds of active volcanoes on its surface. Icy moons in the outer solar system may harbor subsurface oceans. Europa, one of Jupiter's moons, has a smooth surface covered with cracks and few impact craters, suggesting the surface is geologically young and active. Beneath the icy crust, which may be 10 to 15 miles thick, scientists believe there is a global ocean of liquid water, perhaps 60 miles deep. The ocean is kept liquid by tidal heating from Jupiter's gravity. NASA's Europa Clipper mission, launched in October 2024, will arrive at Jupiter in 2030 to study Europa in detail and search for signs of habitability. Saturn's moon, Enceladus, also has a subsurface ocean. The Cassini spacecraft observed geysers of water vapor and ice particles erupting from cracks near Enceladus's south pole. These geysers contain salt, organic molecules, and other compounds from the ocean below. Titan, Saturn's largest moon, may have a subsurface ocean of liquid water beneath its icy crust. These moons are among the most promising places in the solar system to search for extraterrestrial life. Life as we know it requires liquid water, and these hidden oceans may have existed for billions of years, providing stable environments where life could potentially arise and thrive. Volcanic activity continues to shape some planetary bodies today. Volcanism is driven by internal heat, either from radioactive decay, tidal heating, or leftover heat from formation. Earth is volcanically active, with dozens of volcanoes erupting each year. Venus also shows evidence of geologically recent volcanism, though whether it's currently active is debated. Mars has the largest volcano in the solar system, Olympus Mons, a shield volcano about 370 miles wide and 16 miles high, nearly 3 times the height of Mount Everest. Olympus Mons is probably extinct, but some regions of Mars may have experienced volcanic eruptions as recently as a few million years ago. Jupiter's moon Io is the most volcanically active body in the solar system, with hundreds of active volcanoes continuously erupting sulfur and sulfur dioxide. Plumes from these eruptions can reach hundreds of miles above the surface. Volcanism recycles material from a planet's interior to its surface, releases gases that contribute to atmospheres, and creates new landforms. It's a reminder that planets are not static, dead worlds, but dynamic, evolving systems. Impact craters record the history of collisions throughout the solar system. Every solid surface in the solar system is scarred with impact craters, evidence of billions of years of bombardment. The Moon's surface is covered with craters, preserving a record of impacts dating back over 4 billion years. Because the Moon has no atmosphere or plate tectonics to erase craters, its surface is like a history book. Mercury also has a heavily cratered surface, including the enormous Caloris Basin, about 950 miles in diameter, formed by a massive impact early in Mercury's history. Mars has ancient cratered highlands in its southern hemisphere. Earth has relatively few visible impact craters, about 190 confirmed, because weathering, erosion, and plate tectonics have erased most of them over time. But impacts have profoundly influenced Earth's history. The impact that created the Chicxulub crater in Mexico about 66 million years ago caused the mass extinction that killed the dinosaurs. Studying impact craters helps us understand the frequency and scale of collisions, the effects of impacts on planetary surfaces and atmospheres, and the ongoing risks to Earth from near-Earth asteroids and comets. This evidence suggests planetary systems are interconnected networks, not isolated worlds. Planets exchange material through impacts. Meteorites found on Earth include fragments of the Moon and Mars, ejected by impacts and later captured by Earth's gravity. Organic molecules and water may be transported between worlds. The migration of giant planets rearranges the architecture of a planetary system, scattering small bodies and influencing the conditions for planet formation elsewhere in the system. Gravitational interactions create resonances that link the motions of multiple bodies. Even atmospheres can be connected through processes like sputtering, where energetic particles knock atoms off one world and some eventually reach another. The solar system is not a collection of separate, independent objects, but a complex, interacting system shaped by billions of years of gravitational choreography and physical exchange. The study of exoplanets reveals thousands of planetary systems with diverse architectures. As of November 2025, over 6,000 confirmed exoplanets have been discovered orbiting stars beyond our solar system. These planets range from rocky super-Earths to gas giants larger than Jupiter, orbiting at distances from their stars ranging from closer than Mercury to farther than Neptune. Some systems have planets packed much more tightly together than in our solar system. The TRAPPIST-1 system, for example, has 7 Earth-sized planets orbiting a small red dwarf star, all within a space smaller than Mercury's orbit around the Sun. Some exoplanets orbit binary star systems, experiencing sunrises and sunsets from 2 suns, like the fictional planet Tatooine from Star Wars. Studying these diverse systems helps us understand how common different types of planetary architectures are and under what conditions Earth-like planets might form. The James Webb Space Telescope, which began science operations in 2022 and continues observations through 2025, is characterizing the atmospheres of some exoplanets, searching for signs of water vapor, methane, carbon dioxide, and potentially even biomarkers that might indicate life. Not all planets remain in stable orbits forever. Planetary systems can be dynamically unstable, especially early in their history. Gravitational interactions between planets can cause some to be ejected entirely from the system, sent drifting through interstellar space as rogue planets. Computer simulations suggest that our solar system may have originally had 1 or more additional giant planets that were ejected during the chaotic early period. Some exoplanetary systems show evidence of past instabilities, with planets on highly eccentric orbits or planets orbiting in planes tilted relative to their star's equator, both signs of past gravitational upheaval. over very long timescales. Even our solar system's stability is not guaranteed. Calculations show that there's a small chance that Mercury's orbit could become so eccentric that it could collide with Venus or be ejected from the solar system within the next few billion years. The dance of the planets is not eternal. Change, however slow, is inevitable. The formation of terrestrial planets like Earth took millions of years. Unlike gas giants, which can form in a few million years, rocky planets grow more slowly. The process of accumulating planetesimals and protoplanets through collisions takes time. Earth reached most of its current mass within 10 to 20 million years, but the final stages of accretion, including the giant impact that formed the Moon, may have occurred up to 50 to 100 million years after the solar system began forming. After the major accretion phase ended, Earth continued to be bombarded by smaller impacts, gradually adding mass and volatiles like water. The process of differentiation, outgassing, and cooling took hundreds of millions of years. Earth's crust solidified, oceans condensed from water vapor, and the atmosphere evolved. Life may have emerged as early as 3.8 billion years ago, less than a billion years after Earth formed. The timeline of planet formation is long but relatively rapid compared to the age of the solar system, from dust to living world in less than a billion years. We now understand that planetary systems emerge from simple physical laws working over millions of years. Gravity, thermodynamics, angular momentum, conservation, electromagnetic forces at the microscopic scale, and chaos theory at the large scale all contribute. From diffuse nebulas, stars and planets condense. From disorder, order gradually emerges. The process is not designed or guided, but follows inevitably from the laws of physics. Given a nebula of the right composition, temperature, and density, planets will form. The details vary, but the outcome is universal. Across the galaxy, around countless stars, planets are being born right now, following the same fundamental processes that created our own world. We are not special in the universe's grand scheme, but we are part of a vast cosmic pattern, one expression among countless others of the universe's creative power. You're still here, still awake, still drifting with us through these stories. Take a slow breath. Notice how your body feels a little lighter now, as if gravity itself has loosened its grip just slightly. We're traveling through space together, you and I, and everyone listening in the quiet dark, floating through facts like asteroids drifting through the void. There's no rush, no destination, just the gentle momentum of curiosity carrying us forward. Let's continue. Protoplanetary disks contain gaps and rings, revealing where planets are forming. High-resolution images from ALMA, the Atacama Large Millimeter Array in Chile, show that many protoplanetary disks are not smooth, but contain concentric rings and gaps. These features are caused by planets or protoplanets embedded in the disk. As a planet orbits within the disk, its gravity clears a gap by either accreting material directly or scattering it away through gravitational interactions. The material piles up at the edges of the gap, creating bright rings. In 2014, ALMA imaged the disk around the young star HL Tauri and revealed stunning concentric rings, providing direct visual evidence of planets in the process of forming. Since then, dozens of similar disks have been observed. Each disk tells a story of world-building in progress, frozen in time for us to study. These observations, combined with computer simulations, are revolutionizing our understanding of how quickly planets form and how they interact with their birth environment. Pebble accretion may be the key to rapid planet formation. One of the puzzles in planetary science has been how planets can grow fast enough before the gas disk dissipates. Traditional models, which rely on small objects colliding and sticking through random encounters, predict that planet formation should take tens of millions of years, longer than the observed lifetimes of protoplanetary disks. A process called Pebble accretion may solve this problem. Pebbles, objects ranging from centimeters to meters in size, drift inward through the disk due to gas drag. When they encounter a growing planet or planetary core, they can be captured very efficiently by the planet's gravity. Because there's a continuous stream of pebbles drifting inward, the planet can grow rapidly. Computer simulations show that pebble accretion can build cores of giant planets within just 1 to 2 million years, fast enough to capture gas before the disk dissipates. This process may explain how planets form so quickly and why giant planets are common in observed exoplanetary systems. The chemical composition of planets depends on where they formed in the disk. Temperature gradients in the protoplanetary disk determine which materials condense at different distances. Close to the Sun, only refractory materials, substances that remain solid at high temperatures like silicate minerals and metals, could condense. Farther out, volatile materials like water ice, methane ice, and ammonia ice could also condense. This creates a chemical gradient. Mercury is unusually dense and rich in iron, perhaps because it formed very close to the Sun where temperatures were extremely high, preventing lighter elements from condensing. Earth and the other inner planets have significant iron cores but also thick silicate mantles. The outer planets and their moons contain large amounts of ice in addition to rock and metal. The composition of a planet tells us about the conditions in the nebula where it formed and provides clues about its subsequent evolution. Studying meteorites, which are fragments of ancient planetesimals, allows scientists to reconstruct the chemical makeup of different regions of the early solar system. Some planetesimals remained pristine, never incorporated into planets. These objects, preserved in the cold outer reaches of the solar system, are time capsules containing material virtually unchanged since the solar system's formation. Comets from the Oort cloud and Kuiper belt are made of ice and dust that condensed directly from the solar nebula. When these comets are heated by the Sun and develop tails, they release ancient volatiles that can be analyzed spectroscopically. Missions have sent spacecraft to study comets up close. The European Space Agency's Rosetta mission orbited comet 67P Churyumov-Gerasimenko from 2014 to 2016, even landing a probe on its surface. Data from Rosetta revealed that the comet's water has a different isotopic composition than Earth's oceans, suggesting that comets like 67P may not have been the primary source of Earth's water. Primitive meteorites, called carbonaceous chondrites, are also ancient, dating back to the first few million years of the solar system. They contain organic molecules, amino acids, and even microscopic grains that formed in other stars before our Sun existed. Studying these pristine materials helps us understand the raw ingredients from which planets are made. Gravitational interactions can eject planets from their home systems entirely. As we've mentioned, not all planets remain in the systems where they formed. During the dynamic early phase of a planetary system, when young worlds are still finding their paths through space, gravitational encounters can occur. If two planets pass close to each other, they exchange energy and angular momentum. Often, one planet is scattered inward toward the star, while the other is scattered outward. If the outward scattered planet gains enough velocity, it can escape the star's gravity entirely, becoming a rogue planet drifting through interstellar space. Computer simulations suggest that the number of rogue planets in the galaxy could be comparable to, or even greater, than the number of planets orbiting stars. These lonely worlds, untethered from any star, drift in the darkness between stars, perhaps for billions of years. Some may retain moons, or even atmospheres kept warm by internal heat. Others are cold and dead. Astronomers have detected a few candidate rogue planets through gravitational microlensing, where the planet's gravity briefly magnifies the light from a background star. The existence of rogue planets reminds us that the process of planet formation is violent, and not all worlds find permanent homes. Organic molecules are common throughout the solar system and beyond. Life on Earth is based on carbon chemistry, and the building blocks of life include organic molecules, molecules containing carbon bonded to hydrogen and other elements. These molecules are not unique to Earth. They've been found in meteorites, in comets, on asteroids, on Mars, and in interstellar clouds. Amino acids, the building blocks of proteins, have been detected in carbonaceous chondrite meteorites. Polycyclic aromatic hydrocarbons, complex carbon molecules, have been detected in space through their infrared signatures. Saturn's moon Titan has lakes and seas of liquid methane and ethane on its surface, with complex organic chemistry occurring in its atmosphere, driven by sunlight and charged particles from Saturn's magnetosphere. The Cassini-Huygens mission, which studied Titan extensively, found evidence of organic molecules more complex than methane, potentially including amino acids or their precursors. The presence of organic molecules throughout the solar system suggests that the chemical ingredients for life are common and may have been delivered to Earth by comets and meteorites during the late heavy bombardment. Life may have had many chances to begin. Water is one of the most important molecules for habitability. Liquid water is essential for life as we know it. Water is a remarkable solvent, capable of dissolving a wide variety of substances, which allows complex chemistry to occur. The presence of liquid water on a planet's surface depends on temperature and atmospheric pressure. On Earth, water exists as solid ice, liquid water, and water vapor, cycling through the environment. Mars once had liquid water flowing on its surface billions of years ago, as evidenced by ancient river valleys, lake beds, and minerals that form in the presence of water. Today, Mars is cold and dry, but water ice exists at the poles and beneath the surface. If Mars was once warm and wet, it may have been habitable in the past, and fossils of ancient microbial life could be preserved in the rocks. Venus may have once had oceans of liquid water as well, but a runaway greenhouse effect evaporated them, and the water vapor was broken apart by sunlight, with hydrogen escaping to space. Understanding how planets gain, lose, and retain water is crucial for understanding habitability and the potential for life beyond Earth. Habitable zones define where liquid water can exist on a planet's surface. The habitable zone, sometimes called the Goldilocks zone, is the range of distances from a star where temperatures are just right for liquid water to exist on a planetary surface, not too hot and not too cold. The exact boundaries depend on the star's brightness. For our Sun, the habitable zone extends roughly from 0.8 to 1.5 astronomical units, encompassing Earth's orbit. Venus is just inside the inner edge, and Mars is near the outer edge. But being in the habitable zone doesn't guarantee habitability. Venus is hellishly hot, despite being at a distance where water could theoretically exist, because its thick carbon dioxide atmosphere creates a runaway greenhouse effect. Mars is cold and dry, though it was once warmer and wetter. A planet needs the right combination of distance from its star, atmospheric composition, magnetic field, volcanic activity to recycle gases, and perhaps even a large moon to stabilize its axial tilt. Finding Earth-like exoplanets in habitable zones is a major goal of current astronomical research. Planet formation explains why our solar system has its current architecture. The inner rocky planets formed inside the frost line from refractory materials. The outer gas and ice giants formed beyond the frost line where volatile ices were abundant, allowing them to grow large enough to capture gas. The asteroid belt is the remnant of planet formation in a region disrupted by Jupiter's gravity. The Kuiper Belt and Oort cloud preserve the leftover debris. This structure makes sense given the physical processes we've discussed. Migration and gravitational interactions fine-tuned the orbits over time. The late heavy bombardment reshaped surfaces and delivered volatiles. Volcanic activity, tidal heating, and magnetic fields evolved differently on each world, creating the diversity we observe today. Every feature of the solar system, from Mercury's iron core to Neptune's winds to the geysers on Enceladus, can be traced back to the conditions and processes present during the solar system's formation and subsequent evolution. Halfway through our journey, the answer is emerging. Planets form inevitably from chaos. Gravity organizes. Temperature gradients determine composition. Angular momentum creates structure. Collisions both destroy and create. From a shapeless cloud of gas and dust, the architecture of a planetary system self-assembles over millions of years. The process is neither designed nor random, but follows the inexorable logic of physical law. Given the right ingredients and enough time, nebulas will collapse, disks will form, dust will stick, planetesimals will merge, cores will grow, gas will be captured, migration will occur, and worlds will emerge. This isn't speculation. We see it happening around young stars across the galaxy. We see the fossil record preserved in meteorites and cratered surfaces. We feel it in the spin of our planet and the pull of gravity holding us here. Planet formation is one of the universe's most fundamental creative processes, endlessly repeating, endlessly varied, yet governed by the same underlying principles. We're beginning to understand how planets form, but more importantly, we're beginning to understand why they must. Breathe slowly. Feel your body resting here. In this moment, on this ancient planet, 4.5 billion years ago, there was no Earth, only dust. Slowly, grain by grain by grain, that dust became the world beneath you now. Let each breath guide you to realize, time is vast beyond comprehension. The processes we're describing took millions of years. Yet, here you are, a brief consciousness, floating on the result, while the vast universe continues to spin, expand, change. This second, you're breathing, listening, is unique. Cherish the present moment, knowing that right now, your time is unique in the universe, and we continue drifting. The solar system is about 4.6 billion years old, determined from dating the oldest meteorites. Scientists use radiometric dating techniques to measure the ages of rocks and meteorites. Certain radioactive isotopes decay at known rates, serving as natural clocks. By measuring the ratio of parent isotopes to daughter isotopes in a sample, scientists can calculate how much time has passed since the rock solidified. The oldest meteorites, pieces of primitive asteroids that formed during the solar system's earliest moments, consistently date to about 4.567 billion years ago. This is taken as the age of the solar system. Earth's oldest surviving rocks are younger, about 4 billion years old, because Earth's surface has been constantly reshaped by tectonics, erosion, and volcanic activity. Moon rocks brought back by Apollo astronauts are also ancient, with some dating to over 4.4 billion years. These ages tell us that planet formation was a relatively rapid process, occurring within the first 100 million years of the solar system's history. Earth's early atmosphere was very different from today's oxygen-rich air. The first atmosphere formed from outgassing as Earth's interior heated and volcanoes released trapped gases. This early atmosphere likely contained water vapor, carbon dioxide, nitrogen, and smaller amounts of methane, ammonia, and hydrogen sulfide. There was little to no free oxygen. Oxygen is highly reactive, and quickly combines with other elements unless it's continuously replenished. On Earth, oxygen is produced primarily by photosynthesis. When life first appeared on Earth, probably around 3.8 to 3.5 billion years ago, it consisted of simple single-celled organisms. Some of these early microbes, called cyanobacteria, developed the ability to perform photosynthesis, using sunlight to convert carbon dioxide and water into sugars and oxygen. For millions of years, the oxygen they produced was absorbed by iron dissolved in the oceans and by reactions with rocks. Around 2.4 billion years ago, during the Great Oxidation Event, oxygen began accumulating in the atmosphere. Over time, oxygen levels rose to today's level of about 21%. This transformation made Earth habitable for complex aerobic life, including eventually animals and humans. Our breathable atmosphere is a gift from ancient microbes. Plate tectonics on Earth is a critical process for maintaining habitability. Earth's outer shell, the lithosphere, is broken into large plates that move slowly over the underlying mantle. These tectonic plates collide, pull apart, and slide past each other, driven by convection currents in the mantle. Plate tectonics recycles carbon dioxide between the atmosphere and the interior through volcanic outgassing and the subduction of carbonate minerals. This carbon cycle regulates Earth's climate over geological timescales, preventing runaway greenhouse or icehouse conditions. Plate tectonics also generates Earth's magnetic field by keeping the core mantle system dynamic, builds mountains, creates ocean basins, and drives volcanism. Venus and Mars do not have active plate tectonics, and this may be one reason their surface environments evolved so differently from Earth's. Venus's lack of plate tectonics may have contributed to its runaway greenhouse effect by preventing carbon from being recycled into the interior. Understanding why Earth has plate tectonics, while similar-sized Venus does not, is an active area of research. The Moon's gravitational influence stabilizes Earth's axial tilt. Earth's axis is tilted about 23.5 degrees relative to the plane of its orbit around the Sunday. This tilt causes our seasons as different hemispheres receive more or less direct sunlight throughout the year. Computer simulations show that without the Moon's gravitational stabilization, Earth's axial tilt could vary chaotically over millions of years, potentially swinging from near 0 degrees to over 80 degrees. Such extreme variations would cause dramatic climate changes, possibly making it difficult for complex life to evolve. Mars, which has 2 tiny moons with negligible gravitational influence, has experienced large variations in its axial tilt over time, contributing to dramatic climate shifts. The Moon, being unusually large relative to Earth, provides a stabilizing influence that has kept Earth's tilt relatively constant for billions of years. This is another reason why the giant impact that formed the Moon may have been crucial for the development of life on Earth. The Moon is not just a beautiful object in our sky, it's a silent guardian, keeping our climate stable. Jupiter has been called the vacuum cleaner of the solar system. Jupiter's immense gravity deflects or captures many comets and asteroids that would otherwise enter the inner solar system, potentially impacting Earth. The most famous example occurred in 1994 when comet Shoemaker-Levy 9, broken into fragments by Jupiter's gravity, collided with Jupiter in a series of spectacular impacts observed by telescopes worldwide. The impacts left dark scars in Jupiter's atmosphere visible for months. By reducing the number of impacts on Earth, Jupiter may have made the inner solar system safer for life. However, some recent research suggests that Jupiter's role is more complex. While it does capture or eject some objects, its gravitational influence can also perturb the orbits of asteroids and comets, sending some of them toward the inner planets. the net effect is still debated. Nonetheless, Jupiter's presence has profoundly shaped the structure of the solar system, and its influence extends far beyond its own orbit. Saturn's rings may be the remnants of a destroyed moon. As we discussed earlier, Saturn's rings are relatively young, perhaps only a few 100 million years old, which is very recent compared to the age of the solar system. The rings are composed mostly of water ice, which matches the composition of Saturn's moons. One hypothesis is that a mid-sized icy moon wandered too close to Saturn, crossing the Roche limit, the distance within which tidal forces from the planet overcome the moon's own gravity and tear it apart. Another hypothesis is that a moon was shattered by a collision with a comet or asteroid. The fragments spread out into a ring around Saturn. Over time, collisions between ring particles have ground them down into the range of sizes we observe today, from dust grains to house-sized chunks. Saturn's rings are not static, they're constantly evolving. Small moons embedded in the rings, called shepherd moons, gravitationally sculpt the rings into narrow bands and gaps. Cassini's final observations before plunging into Saturn's atmosphere in 2017 showed that material from the rings is constantly raining down onto Saturn, suggesting the rings may disappear entirely within a few 100 million years. Mars once had a thicker atmosphere and warmer climate. Ancient Martian valley networks, dried-up river channels, and lake beds reveal that liquid water flowed on Mars's surface billions of years ago. This requires a thicker atmosphere to provide enough pressure and possibly a greenhouse effect to keep temperatures above water's freezing point. Mars is smaller than Earth, with only about 1/10 Earth's mass, which means its gravity is weaker. Over time, Mars lost much of its atmosphere. Without a strong magnetic field to protect it, the solar wind, a stream of charged particles from the Sun, gradually stripped away atmospheric gases. NASA's MAVEN mission, which has been studying Mars's upper atmosphere since 2014, has directly measured the rate at which Mars is losing atmospheric gases to space today. The loss rate is small now, but over billions of years, it adds up. Mars's declining atmosphere led to falling temperatures and the loss of surface water. Today, Mars is cold, dry, and barren on the surface, though subsurface ice and possibly briny liquid water may exist. If Mars was once habitable, ancient life could have arisen there, and fossils could be waiting to be discovered. Venus gradually developed an intensifying greenhouse effect. Venus is often called Earth's twin because it's similar in size and mass. But the two planets could hardly be more different in terms of surface conditions. Venus has a thick atmosphere composed of 96% carbon dioxide with clouds of sulfuric acid. The atmospheric pressure at the surface is about 90 times Earth's, equivalent to being a kilometer underwater on Earth. The surface temperature is about 900 degrees Fahrenheit, hot enough to melt lead, making Venus the hottest planet in the solar system, despite being farther from the Sun than Mercury. This extreme heat is caused by an intensifying greenhouse effect. Early in Venus's history, it may have had liquid water oceans, but being closer to the Sun, Venus received more solar energy. This caused more water to evaporate into the atmosphere. Water vapor is a greenhouse gas, trapping heat, which caused even more evaporation in a positive feedback loop. Eventually, the oceans boiled away. Sunlight broke apart water molecules in the upper atmosphere, and hydrogen escaped to space, while oxygen combined with rocks. Without water to dissolve and remove carbon dioxide, the atmosphere filled with CO2 from volcanic outgassing, amplifying the greenhouse effect until Venus became the hellish world it is today. Understanding Venus's climate history helps us understand the boundaries of habitability and the dangers of greenhouse warming. Mercury has an unusually large iron core relative to its size. Mercury's core makes up about 85% of the planet's radius, a much larger proportion than any other terrestrial planet. Earth's core, for comparison, makes up only about 55% of the planet's radius. Why does Mercury have such a large core? One hypothesis is that Mercury formed from material unusually rich in iron, though it's unclear why the innermost part of the solar nebula would be so enriched. Another hypothesis is that Mercury suffered a giant impact early in its history that blew away much of its rocky mantle, leaving the iron core largely intact. Evidence for this includes Mercury's low density relative to what would be expected if it were simply a small rocky planet. NASA's MESSENGER mission, which orbited Mercury from 2011 to 2015, provided detailed measurements of Mercury's composition, gravity field, and magnetic field, helping to constrain models of its interior structure. Understanding Mercury's formation helps us understand the diversity of outcomes in planet formation. Uranus and Neptune are still poorly understood compared to the other planets. Only one spacecraft, Voyager 2, has visited Uranus in 1986 and Neptune in 1989. These brief flybys provided most of what we know about these distant worlds. Uranus is unusual in having an axial tilt of 98 degrees, essentially rotating on its side. Its blue-green color comes from methane in its atmosphere, which absorbs red light. Neptune is a deeper blue and is surprisingly active, despite being so far from the Sun and receiving very little solar energy. Neptune has the fastest winds in the solar system, with wind speeds exceeding 1,200 miles per hour. Neptune also has an internal heat source, radiating more than twice as much energy as it receives from the Sunday. The source of this heat is not fully understood, but may involve slow gravitational contraction or chemical processes in its interior. Both Uranus and Neptune have complex magnetic fields that are tilted and offset from their rotation axes. There are proposals for future missions to explore these ice giants in more detail, which would greatly expand our understanding of these mysterious worlds. The Kuiper Belt contains many small icy bodies beyond Neptune's orbit. This region is home to objects ranging from small boulders to dwarf planets like Pluto, Haumea, Makemake, and Eris. These trans-Neptunian objects are remnants from the outer solar system's formation, preserved in a deep freeze for billions of years. Pluto, once considered the ninth planet, was reclassified as a dwarf planet in 2006 when astronomers realized that many similar-sized objects exist in the Kuiper Belt. NASA's New Horizons mission flew past Pluto in 2015, revealing a surprisingly complex and geologically active world with nitrogen ice plains, water ice mountains, and a hazy atmosphere. In 2019, New Horizons flew past a smaller Kuiper Belt object, Arakoth, providing the first close-up look at a pristine, ancient object from the outer reaches of the solar system. Arakoth's smooth, double-lobed shape suggests it formed from a gentle merger of two separate bodies, supporting the idea that planetesimal formation can be a relatively gentle process in the outer solar system. Short-period comets originate from the Kuiper Belt, while long-period comets come from the Oort cloud. Comets are icy bodies that develop bright tails when they approach the Sun and their ices sublimate, turning directly from solid to gas. Short-period comets, which have orbital periods less than 200 years, originate in the Kuiper Belt and have orbits that lie close to the plane of the solar system. Halley's Comet, which returns every 76 years, is a famous short-period comet. Long-period comets have orbital periods of thousands to millions of years and come from the Oort cloud, arriving from all directions. The Oort cloud is a vast, spherical shell surrounding the solar system at distances up to 100,000 astronomical units, nearly halfway to the nearest star. Gravitational perturbations from passing stars, or the overall gravitational field of the Milky Way, occasionally nudge an Oort cloud object into the inner solar system, where it becomes a spectacular comet. Studying comets gives us a window into the primordial material from which the solar system formed. Planets continue to evolve over billions of years. Formation is not a one-time event, but an ongoing process of geological, atmospheric, and orbital evolution. Volcanic activity reshapes surfaces. Tectonic processes recycle material. Atmospheres are gained or lost. Orbits gradually change due to tidal forces and gravitational interactions. Earth's day is getting longer. The Moon is drifting away. Mars's climate has shifted dramatically. Jupiter's Great Red Spot, a storm larger than Earth that has been observed for at least 350 years, may eventually dissipate. Saturn's rings are temporary. The solar system we see today is just a snapshot in a much longer story. In a few billion years, the Sun will evolve into a red giant, expanding and possibly engulfing Mercury, Venus, and maybe Earth. The outer planets will receive more sunlight, potentially making some of their icy moons temporarily habitable. Eventually, the Sun will shed its outer layers and become a white dwarf, a hot, dense remnant. The planets that survive will orbit this stellar corpse in a much different solar system than the one we know today. Our understanding of planet formation has been revolutionized by exoplanet discoveries. Before 1995, we had only one example of a planetary system, our own. The discovery of the first exoplanet around a sun-like star opened the floodgates. Methods like the radial velocity technique, which detects the wobble of a star caused by an orbiting planet, and the transit method, which measures the slight dimming of a star when a planet crosses in front of it, have revealed thousands of exoplanets. The Kepler Space Telescope, which operated from 2009 to 2018, discovered over 2,600 confirmed exoplanets and thousands more candidates. Kepler's data showed that planets are common, that small rocky planets are more common than gas giants, and that planetary systems come in a staggering variety of configurations. The discovery of hot Jupiters, gas giants, orbiting extremely close to their stars, challenged theories that assumed gas giants must form far from their stars. This led to the development of planetary migration theories, which are now central to our understanding of planet formation. Each new exoplanet discovery refines our models and deepens our understanding. We now understand that interstellar space is active, not empty. Between the stars, vast molecular clouds drift, the birthplaces of new stars and planets. These clouds contain complex chemistry, with over 200 different molecules detected through radio astronomy, including water, ammonia, alcohols, sugars, and even amino acids. Dust grains serve as tiny chemical factories where molecules can form on icy surfaces. Supernovae enrich the interstellar medium with heavy elements forged in the cores of massive stars. Stellar winds and outflows from young stars inject energy and momentum, stirring the medium. Cosmic rays, high-energy particles, ionize atoms and drive reactions. The interstellar medium is not a void, but a dynamic, evolving environment, intimately connected to the life cycles of stars and the formation of planetary systems. The solar system's place in the galaxy influences its history. Our solar system orbits the center of the Milky Way galaxy once every 225 to 250 million years, a period sometimes called a galactic year. As we orbit, we pass through the galaxy's spiral arms, regions of higher density where star formation is active. These passages may trigger disturbances in the Oort cloud. sending comets into the inner solar system and increasing impact rates. Some researchers have speculated that mass extinctions on Earth might correlate with passages through spiral arms, though this is controversial. The Sun also oscillates up and down relative to the galactic plane as it orbits, passing through the plane approximately every 30 million years. Our current position is relatively safe, in a low-density region between spiral arms. The Milky Way is also not isolated. It's part of a larger cosmic web of galaxies, slowly moving through space, and will eventually collide and merge with the Andromeda Galaxy in about 4 to 5 billion years. But that collision will be so slow, and the distances between stars so vast, that it's unlikely any stars will actually collide. The asteroid belt could have formed a planet, but didn't because of Jupiter. Early in the solar system's history, the region between Mars and Jupiter likely contained enough material to form a small planet, perhaps the size of Mars. But Jupiter's gravity stirred up the orbits of planetesimals in this region, increasing their relative velocities. Instead of gently merging during collisions, they shattered. Some fragments were ejected from the solar system, some fell into the Sun or impacted planets, and some remain as the asteroid belt we see today. The total mass of all asteroids combined is only about 4% the mass of the Moon, a tiny fraction of what must have been there originally. The largest asteroids, like Ceres, Vesta, and Pallas, are surviving protoplanets that never merged into a larger body. Studying them provides insight into the building blocks of planets. NASA's Dawn mission studied Vesta and Ceres in detail, revealing that even small bodies can be geologically complex. The ancient encounter that formed the Moon may have helped establish conditions favorable for life. Impact events have shaped the history of life on Earth. The Moon's formation contributed to Earth's magnetic field and axial tilt stability. The late heavy bombardment delivered water and organic molecules, possibly providing the ingredients for life's origin. Impacts can also cause mass extinctions. The most famous example is the Chicxulub impact 66 million years ago, which created a global environmental catastrophe that wiped out about 75% of species, including the non-avian dinosaurs. But impacts can also create opportunities. The extinction of the dinosaurs allowed mammals to diversify and eventually gave rise to humans. Impacts continue to this day, though large ones are rare. Near-Earth asteroids are monitored closely to identify potential threats. Planetary defense strategies, such as deflecting asteroids with kinetic impactors or gravity tractors, are being developed to protect Earth from future impacts. Moons often have subsurface oceans warmed by tidal heating. We've discussed Europa and Enceladus, but there may be others. Jupiter's moon Ganymede, the largest moon in the solar system, likely has a subsurface ocean beneath its icy crust. Saturn's moon Titan may have a subsurface ocean of liquid water beneath its surface, despite having lakes of liquid methane on its surface. Neptune's moon Triton, which orbits retrograde suggesting it was captured from the Kuiper belt, has geysers of nitrogen erupting from its surface. The prevalence of subsurface oceans in the outer solar system suggests that habitable environments may be more common than previously thought. Life doesn't require a planet in the habitable zone of a star if tidal heating can provide warmth and liquid water beneath an icy shell. These hidden oceans may harbor life forms completely different from anything on Earth, adapted to high-pressure, dark, cold environments. The heliosphere is the bubble of influence surrounding our solar system. The Sun constantly emits a stream of charged particles called the solar wind. This wind travels outward in all directions, creating a bubble called the heliosphere that extends far beyond the orbits of the planets. The heliopause is the boundary where the solar wind's pressure balances the pressure of the interstellar medium. Voyager 1, launched in 1977, crossed the heliopause in 2012, becoming the first human-made object to enter interstellar space. Voyager 2 crossed the heliopause in 2018. Both spacecraft continue to send back data, providing the first direct measurements of conditions in interstellar space. The heliosphere protects the inner solar system from some galactic cosmic rays, high-energy particles from outside the solar system. Changes in the solar wind can affect the size and shape of the heliosphere, influencing the radiation environment experienced by planets. Understanding our solar system helps us search for life beyond Earth. Astrobiology, the study of life in the universe, relies on understanding how planets form, what conditions allow life to arise and thrive, and where we should look for signs of life. Knowing that subsurface oceans exist on multiple moons tells us where to search. Knowing that organic molecules are common throughout the solar system tells us that life's chemical ingredients are widespread. Knowing that liquid water existed on Mars in the past tells us that Mars might have once been habitable. Future missions aim to search for biosignatures, signs of past or present life. NASA's Perseverance rover, which landed on Mars in 2021, is collecting samples that will eventually be returned to Earth for detailed analysis. The Europa Clipper mission will search for signs of habitability on Europa. The James Webb Space Telescope is analyzing the atmospheres of exoplanets for gases that might indicate biological activity. Each discovery brings us closer to answering one of humanity's oldest questions: are we alone in the universe? The study of planet formation connects to our origins as a species. Every atom in your body, except hydrogen, was forged in the core of a star or in a supernova explosion. The iron in your blood, the calcium in your bones, the oxygen you breathe, all came from stars that lived and died before the sun was born. The dust from which Earth formed included these stellar remnants. Planet formation is not just a process that created rocks and gas orbiting a star. It's the process that created the stage on which life emerged and evolved. Understanding how planets form helps us understand how we came to exist. It places human existence within a cosmic context, showing that we are intimately connected to the universe's grand cycles of creation and destruction. We are not separate from the cosmos but part of it, products of the same physical laws that shape galaxies, stars, and planets. Planetary science is a young field, rapidly evolving with new discoveries. The space age began only in 1957 with the launch of Sputnik. Humans first walked on the Moon in 1969. The first images of Jupiter's moons were captured by Voyager spacecraft in 1979. The first exoplanet around a Sun-like star was discovered in 1995. The Curiosity rover landed on Mars in 2012. The New Horizons flyby of Pluto occurred in 2015. The James Webb Space Telescope began operations in 2022. Each mission and discovery transforms our understanding. Ideas that were once speculative are now confirmed. Mysteries remain, but we're solving them at an accelerating pace. This is an exciting time to study planetary science. Within our lifetimes, we may discover life on Mars or Europa, find Earth-like planets around nearby stars, and perhaps even set foot on Mars ourselves. Planets are not just geological objects, but complex systems. They have interiors, surfaces, atmospheres, magnetic fields, and in some cases, moons, rings, and biospheres. All these components interact, influencing each other in feedback loops that determine a planet's evolution. Earth's climate is influenced by volcanic outgassing, weathering of rocks, the greenhouse effect, ocean currents, ice sheet dynamics, biological processes like photosynthesis, and even human activity. Understanding a planet requires integrating geology, atmospheric science, chemistry, physics, biology, and more. This holistic, interdisciplinary approach reveals that planets are more than the sum of their parts. They are dynamic, evolving systems, endlessly fascinating in their complexity. 3i Atlas has taught us that our solar system is part of a vast galactic exchange, and now we see planet formation the same way, not isolated, but interconnected. Planets form from nebulas enriched by previous generations of stars. Material is exchanged through impacts, migration, scatters objects across the solar system, and gravitational interactions link the motions of planets and moons. The solar system is not a collection of separate worlds, but a single, interconnected system shaped by billions of years of interaction. And beyond, in the wider galaxy, star systems exchange material through interstellar objects like comets and rogue planets. The universe is more connected than it appears. We are part of this great exchange, participants in cosmic processes that stretch across space and time. You might be feeling tired now. That's perfectly fine. Breathe slowly. Feel the cycles. Planets orbit stars. Moons orbit planets. The Sun orbits the center of the galaxy. All are circles, cycles, endless orbits. Like your breath, inhale, exhale, inhale, exhale. A small cycle within the vast universe. You are also part of that eternal movement. Dust becomes planets. Planets create life. Life returns to dust. The cycle continues. You don't need to hold on to anything. Let everything unfold in its perfect order, like planets silently rotating in their orbits, unhurried, unresisting, simply existing. We're almost there now. In the end, planet formation is about transformation. Diffuse gas becomes solid rock. Chaos organizes into orbits. Emptiness fills with worlds. What was scattered becomes gathered. What was formless takes shape. This transformation happens everywhere in the universe, continuously, following the same fundamental laws. It's one of the cosmos's most profound creative processes. Planets are archives of history. Every crater, every layer of rock, every atmospheric gas tells a story of what came before. The Moon preserves impacts from billions of years ago. Mars's dried riverbeds whisper of ancient flowing water. Earth's rocks contain fossils, documenting the evolution of life. By studying planets, we read the universe's history written in stone and ice and air. The process is patient. Grain by grain, collision by collision, year by year, over millions of years, worlds emerge. There is no rush in the cosmos. Gravity works slowly, but inevitably. Time is abundant. The universe waits while planets form, indifferent to impatience, shaping worlds at its own pace. Each planet is unique, yet all follow the same principles. Mercury's iron heart, Venus's crushing heat, Earth's blue oceans, Mars's red deserts, Jupiter's swirling storms, Saturn's icy rings, Uranus's tilted rotation, Neptune's deep blue winds. Each world has its own character, its own story, yet all were shaped by gravity, thermodynamics, and chemistry. The universe builds from simplicity to complexity. Hydrogen and helium, the simplest elements, were created in the Big Bang. Stars fused them into heavier elements. Planets gathered those elements. Chemistry organized them into molecules. On at least one world, molecules organized into life. Life organized into consciousness. And now, consciousness reflects on how it came to be. From hydrogen to thought, the journey is long, but unbroken. We are made of planet-forming materials. The carbon in your cells, the calcium in your bones, the iron in your blood, the phosphorus in your DNA, all were once scattered as dust in the solar nebula. You are reconstituted cosmic dust, given form by planet formation and life's evolution. You are the solar system contemplating itself. Planet formation connects us to distant worlds. Every exoplanet discovered around another star formed through the same processes. Though they orbit alien suns light years away, they're kin to Earth, born from similar nebulas, shaped by similar forces. When we study them, we see family resemblances. The night sky is filled with worlds. When you look up at stars, many have planets orbiting them. Some have rocky planets in their habitable zones. Some have gas giants and icy moons. Each point of light represents entire planetary systems, worlds upon worlds, formed and evolving according to universal laws. Understanding planet formation helps us appreciate Earth's fragility. We live on a thin film of rock and water spinning through space. Our atmosphere is a fragile shell. Our climate is balanced on a knife's edge. Venus and Mars remind us what can happen when that balance shifts. Earth is precious precisely because its conditions are delicate. Yet Earth is also resilient. It has survived impacts, volcanic eruptions, ice ages, asteroid strikes, and dramatic climate shifts over billions of years. Life has persisted through mass extinctions, adapting, evolving, filling every available niche. The planet heals, ecosystems recover, the cycles continue. Earth has a deep strength built from billions of years of planet formation and evolution. The question, how do planets form, is really asking, how did we come to be? Understanding planet formation is understanding our origin story. Before there was life, there were planets. Before planets, there were planetesimals. Before planetesimals, there was dust. Before dust, there were stars. Before stars, there was the Big Bang. Everything connects. Planet formation is still happening. Right now, around young stars in nearby nebulas, dust is sticking together. Planetesimals are colliding. Protoplanets are growing. Gas is being accreted. New worlds are being born while we sleep. In Orion, in Taurus, in countless other star-forming regions throughout the galaxy. The creative process never stops. Every sunset you see is light from a star created by planet formation processes. The Sun exists because a nebula collapsed. The planets formed from the disk around the Sunday Earth stabilized in the habitable zone. An atmosphere formed and evolved. Life emerged. And billions of years later, you stand on this world, watching sunlight filtered through that atmosphere, painted across the sky. The sunset is an echo of planet formation. We are a young species on a middle-aged planet. Humans have existed for only a few 100,000 years. Civilization for only 10,000 years. Science for a few hundred years. We've known about planet formation for perhaps a century, yet we've learned so much, so quickly. Imagine what we'll understand in another century, another millennium. So, could planet formation teach us about ourselves? It already has. It shows us that we're temporary, that Earth is temporary, that even the Sun is temporary. But it also shows us that we're part of something vast and ancient, connected to cosmic cycles billions of years old. We're children of the stars, dwellers on a fortunate world, brief sparks of consciousness in an unimaginably large universe. The answer to how do planets form is both simple and profound. Gravity gathers, temperature sorts, chemistry binds, time transforms. From clouds to worlds, the universe organizes itself, creating complexity from chaos, structure from randomness, beauty from physical law. This knowledge changes how we see the universe. The stars are no longer just distant lights but suns with planets. Those planets are no longer just dots but worlds with histories. Space is no longer empty, but filled with the process of creation. Everywhere we look, the universe is building, evolving, transforming. It also changes how we see ourselves. We're not outside observers, but participants. Not separate from nature, but products of it. Not watching the universe, but experiencing it from within. We are the universe's way of knowing itself. Planet-formed matter, capable of understanding planet formation. The diversity of planets reminds us that outcomes vary. The same starting conditions can produce Venus or Earth, depending on subtle differences. Small changes early on can have profound effects later. Planets teach us about path dependence, about how history matters, about how the present is shaped by the deep past. Yet underlying this diversity is unity. All planets, all moons, all asteroids and comets, all formed from the same basic ingredients, governed by the same laws of physics. The variety is infinite, but the foundation is shared. We are all made of the same stuff, just arranged differently. This is comforting in a way. It means we're not alone in being subject to physical law. The universe doesn't single us out. The same gravity that shaped Jupiter shapes our bodies. The same thermodynamics that drove planetary differentiation drives our metabolism. We belong here. Planet formation is the story of home. Every world is home to the forces that shaped it. Earth is home to us, shaped by the same processes that shaped all other worlds, yet uniquely suited for life. We evolved here because this planet allowed us to. We fit because we were shaped by the environment that formed alongside us. When you rest tonight, you rest on a planet 4.5 billion years in the making. Beneath you are layers of rock laid down over eons. Above you, an atmosphere filtered through billions of years of life. Around you, a magnetic field generated deep in the molten core. You are cradled by a world created through cosmic processes. The real change isn't in understanding how dust becomes planets. It's in recognizing that you are part of that process. You are made from that dust. You walk on that accumulated rock. You breathe that evolved atmosphere. You exist because planet formation succeeded here, because Earth found the right orbit, the right size, the right chemistry. In answering how do planets form, we've discovered something deeper. Planets don't just form in space, they form us. We are planetary beings, shaped by the world we inhabit, carrying the history of the solar system in our atoms. Planet formation is not a distant cosmic event. It's the story of how we came to be here, alive, conscious, gazing up at the stars and asking how it all began. That is the answer. That is the gift. And so, our quiet journey through planetary formation comes to a gentle close. We've traveled from collapsing nebulas to spinning disks, from microscopic dust grains to worlds large enough to hold atmospheres and oceans, discovering along the way that the universe is endlessly creative, patiently building worlds from nothing. From the heat of newborn stars to the frozen edges of the solar system, we've glimpsed how planets are both diverse and united, shaped by the same forces, yet each following their own path. Planets remind us that transformation takes time. Much of the universe's most profound work happens slowly, invisibly, grain by grain, in the cold darkness between stars. They teach us patience, resilience, and the power of gradual accumulation. Without gravity's patient pull, without billions of tiny collisions, without time's long work, there would be no worlds, no oceans, no life. By pausing to notice, we glimpse the extraordinary in the ordinary, that the ground beneath us is ancient dust, organized by gravity into a living world. And now, in these final minutes, take the deepest breath you can, as deep as possible. Think about unity, of every atom, every event, every moment in the universe. You are not separate. You are a link in the endless chain. Think about the unity of every atom in the solar nebula, where all the planet's materials once drifted together. Your atoms were there too, mixed with the dust that became Earth. You are made of planet-forming material, shaped by the same forces. Let your entire being dissolve into the gentle rotation of worlds, into the slow orbit of planets around the sun, into the ancient patience of gravity. Prepare for deep sleep, no boundaries left, only peace. If this gentle journey through planetary formation brought you peace tonight, perhaps share it softly with someone else who's searching for stillness under the stars. It might be exactly what another restless mind needs to finally let go and drift. One quiet share, one peaceful night at a time. But there's no need to do anything now. Nothing at all. You've traveled far tonight, farther than most journeys take you. You can allow these thoughts of planets and nebulas to fade now, like evening light slipping below the horizon, leaving only the deep calm behind. Let your breathing deepen. Let your body feel heavier, as if Earth's gravity is gently pulling you down into the mattress, holding you safely. If sleep comes, let it carry you like a leaf floating on a slow river, smoothly, inevitably, into a realm where time and weight no longer matter. If your eyes are still open, the next video is waiting for you, ready to continue the journey. But if they're closed, stay there. Stay in the darkness that feels safe and warm. Tomorrow, planets will still be forming around distant stars. Gravity will still be gathering dust. The universe will still be creating worlds. But tonight belongs to stillness. Rest well, traveler. And remember, you are made of stardust, organized by billions of years of cosmic evolution into something capable of understanding its own origins. That is extraordinary. That is enough. Good night.